Good morning, Fantasy Meet Computers. How's everybody doing this morning? Hopefully you're okay. Hopefully life is doing you a solid this morning. By, I don't know. I just thought I'd say it. How is everybody today? Hopefully you're okay. Etc., etc. He's like, you already asked that. Shut up! This is my live stream, isn't it? Friggin' normies, man. Question 3 is a toughie. Good luck. This has been haunting me. Yeah, I would say that easily question 3 on assignment 4 is the most difficult problem of the course. Like, there's a reason this assignment only has 3 questions. But I think it's an extremely valuable exercise. If you're having, yep. Yeah, Shell Sword is not too bad in comparison to this one. But, I think my solution for it is somewhere in the vicinity of 90 to 110 lines of code, something like that. Watched some videos on graph theory to understand its applications, and now I'm invested. Right? Yeah. I just read it. I don't even understand what 3 is saying. Oh, well, that would be a first barrier to entry, wouldn't it? All right, okay, fine. I will explain question 3 to you, because I've hyped it up so much. So it's really just more string processing. All right? I'm only gonna say this once, so pay attention. And anybody who asks me later, I will tell them, go watch the video from Remembrance Day. Happy Remembrance Day, by the way. And yeah, so. Question 3 is in dire need of Python's eval. Yeah. So, let me read you the question. Write a C function, simple parse, that, taking an algebraic expression expressed in a string, calculates the number represented by that expression. You will need to account for the following. Number 1, literals of type integer. You do not have to worry about any prefixes like 0x or postfixes like L. It's just 3 numbers, 3 integer digits. I forgot today was Remembrance Day. Whap, 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 whap. Nice one. I suppose I should be wearing a poppy on stream, shouldn't I? Give me a second. There we go. Quick, well, I was going to say something good about Python. No! No Python support in this class! So, what are literals? Literals are just numbers. So, literals are things like, oh my god, that's just going to be unreadable. Alright. Maybe top, bottom? Anyway. So, a literal is anything like 1, or 7, or 567. It's just a number. A literal is a number. I'm assuming question 3 relies pretty heavily on string token. That's certainly one valid approach, yes. If this was my high school, we would go to the assembly now. Good times. Yeah, So it's possible that a number of you sort of aren't like culturally Canadian who are in this class. So after I explain this question, I'd like to take a few minutes to just explain Remembrance Day and the significance of it. If you're new to Canada, it might be interesting for you to understand what today is about. But so simple expression parsing. So yes, so you need to take into account literals of type integer. Fortunately, these are the only literals that you have to deal with. So basically what I'm saying with that is that you have to be able to, your expression needs to be able to handle numbers of up to 3 digits for any of the numbers. They can be up to 3 digits. You don't have to worry about negative numbers either. You have to worry about 5 operations, 5 integer operations, addition, subtraction, multiplication, integer division, and modulus. Should we assume a maximum number of digits for each literal? Yes, so each literal will be between 0 and 999 inclusive. You may assume that an expression will contain no more than 8 literals and 7 operators. So the expression itself is no longer than 8 literals. Like you have only 8 numbers will be in this expression, up to 8 numbers. You may assume no literal will be more than 3 digits. I said that already. Your algorithm must account for variable amounts of blank space between characters. So I'll tell you what I mean by that. So an example expression, 3 plus 5 minus 6. All right, 3 plus 5 minus 6. But what I mean to say when I say you need to be able to account for a variable amount of white space is this should be parsable. That should be parsable. Basically, the only time you don't have, like, you won't have space in the middle of a number, because obviously not. But between a space and an operator, there may be any number of spaces, including tab characters. So you have to write an algorithm that throws away the white space, basically. Personally, I think that's an easy pre-processing step. Question. So is what the question is saying that it'll give us a string like 12 plus 33 times 22 plus 99 minus 13, and we need to do something to evaluate it? Yes, that is exactly what the question is asking. Basically, it's like take in an integer expression and turn C into a calculator. Your program must execute operations in the expression according to the standard order of operations, where multiplication and division bind more tightly than addition and subtraction. Modulus is bound at the same level of tightness as multiplication and division. Yes. So yes, that last bit is BEDMAS applies. And insofar as BEDMAS applies, we're assuming that modulus is in the same group with division and multiplication. Because, you know, multiplication and division are at the same level, right? Can we create separate functions to call in simple parse? Yes, I would recommend it. Yeah, absolutely. In fact, that would be an extremely useful way to decompose the algorithm. That would be using coding correctly, would be to write, like, some of these sub-operations are obviously their own function, so it would be excellent for you to be able to write other functions. In general, I don't care, I actually would like to encourage you to write as many other functions as you think are necessary. We just need the top-level function that's being called by the autograder to not have any modifications in it. Because if there are any modifications in that function, then, you know, it breaks the autograder, and then we have to go fix it manually, so please don't. However, once you're inside of that function, you can create and call as many other functions as you like. That's absolutely fine. There won't be any brackets in the expression, though, right? That's correct. So there are no brackets. No, you don't have to worry about brackets. Yeah. So, with respect to an approach to solving this problem, I think I'll let you guys try it first. But will you get the size of the expression put into simple parse? Yeah, there we go. Yes, you can use string length to find the length of the string. That doesn't necessarily tell you how many integers there are in it, right? But yeah, so all of the questions in this assignment are sort of expecting you to use the string parsing library and the character, like the string and character libraries that we were discussing a week or two ago. It's my expectation that this is where you're learning how to use them properly. I know, in particular, question 2 here, if you use the string parsing, like, not only, like, if you use string parsing libraries and, not just the string parsing libraries, but also, like, format strings. If you use format strings plus the string parsing libraries, question 2 is, like, 6 or 8 lines of code. And if you don't do that, it's, like, 100 to 150 lines of code. So, use the libraries. Use the source, Luke. Will I go over examples to help you do the assignment? I mean, that's kind of what I did in lecture already. Hope y'all were paying attention. Yeah. No, I just thought I'd take some time to describe this problem. I really do think that the best way to go, like, the way that you will get the most out of this question as a learning exercise is to try the question out without making too many assumptions about what's the correct way of going about this problem. This is a sufficiently open-ended problem that you can come up with your own solution to it, and if you solve the problem, this should be one of those problems where you really feel like you've accomplished something. So, yeah, I'll tell you one thing though about this expression parsing, this question 3. I'll give you a little bit of I'll give you a little bit of a hint. If this question should prove too much for you, the test cases have been set up such that there are points available if you can process something very simple, like, 5 minus 7, or 9 divided by 2, right? So, basically, you can expect the points for the question to be linearly distributed as the complexity of the expression increases. So, like, there are a certain amount of points available if you can handle 2, there's a certain amount of points available if you can handle 4 integers, and if you can handle all 8, then, there you go. And it's like you can, if you just wanted to do, like, a very simple version of this that only, like if you constrained this to be, like, 1-digit integers with two 1-digit integers with one expression, like, that solution is relatively easy. But, in order to handle, like, the whole thing, you have to be able to handle the most complicated one. And the code stub has been included with examples of varying complexity. Is division integer division? Yes. Yes, it is, my friend. Yes, it is. So, The beauty of question 3 is how many approaches you can take to solve it. Yeah, it really is like... I know this seems like a trite example, but this is the closest I think we're going to come in this class to real software development. So, have fun. If you can accomplish it, if you can make it through this question, then you should feel accomplishment. And if you don't get it, then hopefully you get enough points to, not do terribly. But I don't necessarily expect everyone in the class to be able to get that question completely. I hope that most people in the class would be able to get, most people in the class I hope will be able to get 8 points out of 16. But anyway, I wanted to talk about Remembrance Day for just a little bit of time because I think it's important. So, for those of you who may not be aware, in Canada, on Remembrance Day, which is always November 11th, we commemorate the end of the First World War. It's considered polite to wear a poppy. I think that it sort of starts November 1st. The period from November 1st to November 11th is sort of the poppy wearing season. So if you're going out in public, you should wear a poppy. The poppies are sold. You can get them pretty much anywhere. Grocery stores, pretty much any big store will have a poppy tray, and Tim Hortons and all of that. And you pay $1 and you get your poppy, and the money goes to support war veterans. So it's to commemorate the end of the First World War. That was what it was put in originally. That's what its original purpose was, but as we kept getting in wars, Remembrance Day has kind of shifted to be more a commemoration of war in general. The spirit of the occasion is not a glorification of violence, but a recognition of the sacrifices made by our men and women of the service, of the armed forces. And, some of the wars that we were in the 20th century were really, really horrible affairs. And if you have any spare time today, I recommend just browsing Wikipedia or something to see how horrible the First and Second World Wars were. I was actually, recently, a few years ago, there came out a video, I believe it's called 1917, and it's about the First World War, and it's actually really interestingly shot cinematically, because it's the entire movie is one continuous shot, which is a very interesting thing. But yeah, that movie, I think, does a really good job of illustrating the horrors of the war. But yeah, so on November 11th, at 11 o'clock in the at 11 o'clock in the morning, we have a moment of silence. We have a full minute of silence to remember our war dead, and also to it's kind of specifically for the war dead. They will not grow old, as we that are left grow old. But yeah, so I would encourage you, if you have any interest in it, to attend. I believe the university is having a Remembrance Day live stream, which is, of course, kind of lame, in the same way that my lectures are kind of lame when they're live streams. Like, it's much better to be there in person. But yeah, so... Yeah, anyway, so that's Remembrance Day. If you didn't know what it was, now you do. So, yeah. Anyway. So, so we should continue talking about our lecture material, shall we? So last time we were talking about linked lists. And, we got, I don't think we quite got to doubly linked lists. We also didn't quite get to why you would use a linked list versus an array. And, so we should talk about that, because, you know, it's like I give you this data structure and I don't even tell you what it's good for. You know? But to be fair, we did do an example in class, and people had lots and lots of questions about that example, so I think it was still a class well spent. So, so linked list versus an array. So this linked list thingy, it seems to function basically in the exact same manner as an array, so why wouldn't you just use arrays, right? Why go to all the bother? Seems like a lot of work just to make something that roughly functions like an array anyway. So, the advantage of the linked list is that it is not stored in contiguous memory. It can be dynamically grown or shrunk without having to copy the whole array. So think about it this way, right? If you have an array and you want to insert something in the middle and like have the array expand as a result, that's impossible with static arrays, and it's only possible with dynamic arrays if you use realloc, if you use a reallocation mechanism. Whereas, with a linked list, all you have to do is instantiate a new node and update the pointers. That's it. Because the next node is indicated with pointers, and those pointers may be modified, we can insert an element without having to move any of the other elements in memory, which saves a heck of a lot of time. The amount of time that it saves is proportional to the size of the data structure you don't have to move. Of course, there are some drawbacks. Because nodes are not stored in contiguous memory, we can't perform pointer arithmetic to find the next, to find any particular index. So instead, so basically what this means is we can't use like regular style indexing, right? You can't just use the square brace notation over a linked list, obviously. So instead, we have to write an algorithm to follow the node pointers. This is also known as traversal. This means that finding the record at index I takes I operations, whereas an array can do it in one operation. So the advantage that an array has over a linked list in terms of speed is if you know the beginning address of an array, you can find any index of that array in one operation, because all you have to do is perform pointer arithmetic. With a linked list, if you know the start of the linked list and you know that you want to find the sixth element, you actually have to you have to virtually traverse. You have to follow the pointers through element 0, 1, 2, 3, 4, 5, and then find 6. So you can't just directly jump there. You have to follow the data structure. Whether or not this is advantageous, right? Whether this is an engineering trade-off, right? Arrays are better for certain operations. Linked lists are better for other operations. Which structure is the correct one for any particular situation is going to be dependent on that situation. So, circling back to question 3, should we assume there is one less operation than there are literals? Yes. You can assume that safely. You can assume that there are no dangling operators. So you can assume that there's nothing like 5 plus 7 plus with nothing, that's a bad case. That won't happen. You can also assume that things like 3 minus divide 7 won't exist. Right? You can also assume that is a bad case, and you don't have to process it. Yeah. So for the doubly linked list, singly linked lists are awesome, but you can only traverse them in one direction. That is to say, once you have gotten to element 6, unless you kept some kind of secondary memory log of where you were previously, it's impossible to get back to where you were. This problem is solved by the doubly linked list. So a doubly linked list is a singly linked list with one added condition that each node has an edge that points back to the one that points to it. No node may be pointed to more than twice. So essentially, what we're doing is we're adding a next and we have a next. Singly linked nodes have or singly linked lists have a next pointer. Doubly linked lists also have a previous pointer. Right? So, yeah. To David's question, will you get negative numbers? No, you will not. Your result might be negative, but you won't receive it in the string. Right? Like, something like 5 minus 10 is a valid input string. The result will be negative 5, but a negative number will never be a literal. Remember that the numbers are between 0 and 999 inclusive. So, with the addition of one more pointer, previous, we have made a singly linked list into a doubly linked list node. So we'll never get something like negative 10 divided by 5. Correct! You will never get anything like that. The first element's previous pointer will point to null, and the last element's next pointer will also point to null. While doubly linked lists increase the amount of bookkeeping that we have to do and increase the amount of memory slightly, it makes the list traversable in either direction, which can be very important for some applications. Particularly applications which have to trace back and forward through a list of things. So, this is how it would look in Big Blockovision. So, we have a pointer to the first element of the linked list. We would probably call this head or something like that. We have name, email, and pinball, next and previous, all collected together into one node. The next pointers will always point to the next node in the sequence. When you get to the end, the next pointer will point to a null value. Also, null is just a joke on my part. And the previous values, the first previous value will point to a null value as well. It won't point to a null value, it will have a null value, right? Maybe that's a little bit confusing. I should have put null as a sub thing in here, I suppose. But can we add this to the example code we did last time? Yeah, I think we could do that reasonably easily. Previous will previous, each node, the previous pointer points to the last element in the list, right? So that's good. Wait, where does modulus go in the? It's in the question. It's not part of bad mess. It's in the question. Read the question. So let me open up. So the first block previous pointer always points to null. Correct. because it has no previous value, right? It's the first one, so there's nothing before it. So it just points to null. Right. So here's our singly linked list. Let's turn it into a doubly linked list. So, struct SLL. I suppose I should call it DLL, but whatever. Prev. So, it's really quite easy. So when we're setting the head, setting the various fields of the head, we do head previous is equal to null. And there we go. That's how you do it for the first one, right? For this guy, which is the second node, head next previous is equal to the address of head. Right? And for this guy, head next previous is equal to the address of head next. You might have to bracket this. I think you have to bracket that. But yeah, there we go. And there you go. That's all you need to do to turn a singly linked list into a doubly linked list. Right? Does this make sense? So for each, all we've done is we've taken the singly linked list and added a new field inside of the structure, which just records a pointer to the previous element in the list. This makes the list traversable in either direction. So there we go. Wonderful. So let's talk about, and now for something completely different. Trees! So, let's talk binary trees. Binary trees are an extremely, extremely useful type of thing, right? Question, why do we have to make the first one point to null? I'm still confused about that. Because it has no previous, right? So, think about it. It's the first element in the list. What comes before it? Nothing. Nothing comes before it. Because it's the first element, that's the definition. So, because there's nothing before it, we just set it equal to null. So you can tell if you have a pointer to an element in a linked list, a doubly linked list, and you're not sure which element in the linked list this is, you can tell if it's the head by seeing if its previous pointer is null. So, binary trees. A binary tree is an acyclic directed graph where each node may be connected to at most two other nodes. Trees have a root node, here R, so a root node R. The root of the tree is the node to which no other node points. For every vertex V, there is exactly one path to that vertex from the root node. This is a consequence of it being an acyclic graph, but it's also, like, if you compare this guy to the graph, like the directed acyclic graph we had here, you'll notice that you have the possibility of a node being pointed to by more than one other node, right? So you can have sort of divergence and convergence in the graph, but in a binary tree, you're not allowed to have convergence. All you're allowed to have is divergence. So the thing gets more and more split up as time goes on, right? So each node has exactly one parent, except for the root, and up to two children. So that's some nomenclature that we usually use with trees. Take, for example, this guy right here, right? This V, its parent is root, and it has two children, this one and this one. So, binary trees have at most two children, n-ary trees have at most n children, but we're going to just worry about binary trees for the moment. So, binary trees. Some more nomenclature for you. So trees are extremely useful, and like you can't really consider yourself a programmer unless you have worked with trees, you know? So a leaf node in a tree is any node in the tree which does not point to any other node. So you can think of them as the termination points of the tree, right? So all of them on the bottom here in our example. A stem node is any node in the tree which does point to other nodes. So basically anything at the third tier, the second tier, or the first tier here. These are all stem nodes, and all of the leaf nodes are here. This doesn't have to be the case. It just, like, for example, this is still a valid binary tree if this node here didn't exist. You know? If I were to just pull out my magic marker, cross this guy off, this would still be a valid tree, and this guy here would be the would be a leaf node. But since we're not in that situation, yeah. So the depth of a tree is the number of nodes in the longest branch, i.e., the distance from the root to the furthest leaf in nodes, measured in nodes. The nodes of a tree are organized into levels. All the nodes of the same distance to the root node are at the same level, right? So you can kind of organize your tree. Normally, when you're drawing out a binary tree, you kind of put all of the nodes at one level on the same line, on the same horizontal line. It's just like a stylistic thing. The width of a level is the number of nodes in that level. So in this case, our widths are 1, 2, 3, and 4. And a set of n greater than 0 disjoint trees is called a forest, which is not really relevant at all to the course or anything. I just think it's hilarious that they call a group of trees a forest, you know? So, whereas a singly linked list only has one next pointer, the binary tree has two next pointers. By convention, we call these right and left. So, a binary tree will have left and right, as well as some int value. One interesting property of trees is that they are a naturally inductive data structure. That is to say, both nodes pointed to by left and right can be rightly considered roots of their own subtrees. Therefore, this is a natural application for recursive algorithms. So basically, what's my shortcut? Is it 3? Yeah, it's 3. So basically, if you were to not consider this guy and only consider this guy, right, this is its own subtree, right? This structure that I've circled is a completely valid binary tree in its own right, with this as the root node, right? That means if you're writing an algorithm for a binary tree, which you're going to have to do on assignment 5, if you write an algorithm that deals with a root node and then passes itself along to both children, computes that, and then passes its results back up to the root node, and then, like, processes some final thing, and then passes that on. That is how a recursive algorithm works over a binary tree. Because, you know, when you pass, like, when this guy asks this guy for a result, you know, this guy's going to ask this guy for a result. This guy's going to ask this guy for a result. And finally, this guy's going to pass it back, going to go down this route, ask this guy, you know. what I'm illustrating to you here is a thing called depth-first search. But you don't have to... Well, we have slides on depth-first search. So, yes. So, let's get immediately into it and design a tree summing algorithm. So, let's design an algorithm to recursively sum all of the values in a tree. The sum of a tree is the sum of the left tree, the right tree, and the value of the root node. So that's our recursive definition of sum, right? So the way that you can think of it, if I'm trying to find the sum of all of the values in this tree, I take the value of the root node, right? I set that aside. I then compute the sum of this subtree, compute the sum of that subtree, add all of them together, bam, you've got the algorithm. Because we know all we have to say is we just want the sum of this subtree, because the algorithm to compute the sum of this subtree is the same algorithm as compute the sum of the entire tree, if we define it like that. Is this what you were describing? Is what you were describing similar to doubly linked list? Yeah, you can also do this with doubly linked lists. You can definitely also write recursive algorithms for doubly linked lists, for sure. Most of these graph problems can be solved my position as a, as a mechatronics / software engineering / comp sci guy, my opinion is that anytime you have a graph type problem, you should be looking for a recursive solution. That's my... recursive solutions just work better and are more reliable under these circumstances, but they require you to think differently about programming. So, yeah. So here's the algorithm spelled out a little more explicitly. So, we are examining a node. We know we can examine the left and the right tree, right? So if the left tree doesn't exist, i.e. the left pointer is null, then its sum is 0. Makes sense, right? Does the depth of the tree count the root node? Yes. Yes, it does. If the left tree does exist, we recursively call the summing function on the left tree, considering the node pointed to by the left pointer to be the new root node of the recursive call. We then hold on to the return value for later. We don't have to worry about actually computing the sum. We can just give it the same algorithm. This same algorithm will work on the subtree. We then repeat steps 2 to 3 with the right tree. So if the right tree if the right pointer points to null, then the sum is 0. Otherwise, we call the summing function on the right tree with the pointed to node being the root node. We then add the results of step 2 and 3 to the value of the root node and return this value. So here is an example. Summing the values in a tree. So, I think I may... My brain is telling me that I screwed up the math here somewhere, somehow. So, hopefully, I didn't. But maybe I did. Anyway. So here's a tree. We've got 19, 8, 29, 81, 80, 66, and 67, right? So we're trying to sum this whole thing. First, we examine the left node. The left node is here, 8. So we perform the same algorithm over this subtree, right? So, 8 examines its left node. It's not null. So it says, okay, if there's actually something there, go compute the sum of it. So we go to 81, right? We now examine, is there a left tree? No. Is there a right tree? No. Okay, so we add 0 and 0 to 81. 81 gets returned back up the tree. So now that 8 has dealt with the left side, it can deal with the right side. So it's like, okay, right side, do you exist? It's like, yes, I exist. All right, go sum yourself. So you go down to 66. 66 is like, okay, do I have a left node? No. Do I have a right node? No. Okay, I just returned my value then. So it returns 66 up the tree. So the value of this node then becomes 81 plus 8 plus 66. Now, you know, the implication in this diagram is that we're overwriting the values of nodes as we're doing this. That's not necessary. In fact, it's probably not recommended. It's purely for visual. It's purely for the visual flair. Yeah, that's it. Yeah, thank you. I made an addition error. Oh my gosh, we found it. Okay, you know what? What time is it? I think I fixed this in like the 1xc3 slides. I don't know. Maybe I didn't. It will take. Yeah, it's 1:55. It'll. You know what? I'll write it in my book, and I will have it fixed for next time. I'm sorry. Fix. Bin tree. Some. 2MP3. I apologize. It's kind of silly to make such a silly math error. So anyway, so imagine that this is 155 then. So that value gets passed up to the root node. The root node then looks down the right side. And it's like, okay, so right side, I've got 29. 29, you exist. Go sum yourself. 29 says, okay, let me see. I have no left node, but I do have a right node. So let me see what the right node is saying. So it's like, right node, go sum yourself. So the right node says, okay, I am 67. I have neither left nor right trees. So 67 is what I return up the tree. So, having received the value of 67, this node then smacks those two values together and passes the result back up the tree. Again, the addition error has been carried through, but this guy at the top is then like, okay, left tree is dealt with, right tree is dealt with, smack them together, and the sum is, you know, again, incorrect because I made that addition error, but, you know, I can't believe I made that addition error. That's such a stupid... And they let me teach classes, I tell you. So... This example overwrites node values with the result of the summation. This is mostly for demonstration purposes. A real algorithm wouldn't overwrite node contents like this. So, question. If a node has one child, do we assume it is left or right, or does it not matter so long as we are consistent? It doesn't matter so long as you're consistent. And actually, it doesn't matter at all. According to this algorithm, because any, like... So, let's assume... I did it with like 29 having 67 along the right tree. But if it were along the left tree, you would still be invoking the same summation function, right? It's just like, would it be 0 plus 29 plus, 67? Or would it be 67 plus 29 plus 0? It doesn't matter, right? Addition is commutative, so it doesn't matter. Yeah. And, like, if you're talking, like, in general construction, like, as a general rule of construction, it really, like, for a binary tree like this that has no additional constraints, it doesn't matter. But for some types of binary trees, you will sometimes see they have additional constraints where it matters. I believe we're going to do... Like, we're going to touch briefly on binary search trees here. Yeah, so in some cases it will matter. In most cases it won't. But yeah. But that's class. Any questions? I know I'm throwing a lot of algorithm stuff at you, but, like, as algorithms content goes, this is really, like, the bare bones basics. I'm doing this in... in anticipation of you guys getting into your algorithms course next semester. Hopefully, if you have been introduced slightly to this manner of thinking about problems, you won't be completely bulldozed when you take, 2MD3 next semester. To MD3. That's kind of funny because, like, in comp sci, I teach 1 MD3. So it's like, you know. Yeah, I was looking at the sessional postings for next semester are currently under application. So, I threw an application at it, but I kind of I think I have to hold myself to having only teaching 2 courses next semester, rather than 3. So, and I've already got 2 that I've already taught that are happening that semester. So I think probably I won't be teaching 2 MD3 with you fine people, you fine folks. But, you know. But otherwise it would have been a possibility. How would a node know if the single node it points to is left or right, since left and right can't really exist without each other? Well, in terms of actual implementation details, your pointer is always going to be in one of these 2 slots, right? Like, when you actually go to implement it, like, that's like a mathematical abstract detail that doesn't make its way into the actual code implementation, right? When it's a code implementation, it's not like, you know, you have a, you know, it's not like there's a third pointer here for, like, neither left nor right, right? Like, it's always either going to be left or right, unless you were to, like, throw another pointer in that you only allocated to when there was neither left. Like, when, like, why would you add a third pointer for use only when, you know, you only had one subtree you were pointing to? Why wouldn't you just use left or right? Particularly, why wouldn't you just use left or right when that still works just as well, right? You don't need it. It just adds extraneous, like, it just complicates the issue without actually adding to your ability to solve problems. Any other questions? What room are office hours in again? ITB 102. Office hours officially start at 1:30 and end at 3:30. Incidentally, Mechatronics 2MD3 was added to the program because all of the Mechatronics people were getting absolutely crushed in 3rd and 4th year because they don't have the algorithmic, like, they don't know the algorithms materials that's sort of required at that point that all of the software engineering students do have, you know, when the Tron people take all of their courses that are cross-listed with the software engineering people. The one thing about the poppies is that they're just on just a straight pin, so they fall out very easily, which is actually a design choice. It's to, you know, if you lose your poppy, you're supposed to go get another one, so it's supposed to generate more money for the Legion. I think that's what it is anyway. But if it bothers you that the regular poppy falls out, you can always get one of the ones that's like got an actual pin, you know, with the backing. Yeah, alright, well, take her easy, folks. If you're gonna swing by office hours, then I'll see you at office hours. But yeah, take her easy.